All right, use perpendicular bisectors. So our learning targets are to use the perpendicular bisector theorem to find the missing side of a triangle, apply properties of perpendicular bisectors of a triangle to find missing measures, and to find or construct the circumcenter of a triangle. So first we need to understand fully what a perpendicular bisector is. So a perpendicular bisector is a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. So notice CP is a line, AB is a segment. This little box tells me it's a right angle, so these two, line and segment, they are perpendicular. And these two dashes indicate that these two pieces of AB are congruent, which means that P is the midpoint of AB. So CP, line CP, is the perpendicular bisector of AB. Now, the other vocabulary word we need to know is equidistant, and it's exactly like it sounds. It is the same distance away from two figures. All right, so our perpendicular bisector theorem tells us that if we're in a plane, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So CP is the perpendicular bisector of AB. And what that means is point C is the same distance away from A as it is from B. So if CP is the perpendicular bisector of segment AB, then CA is equal to CB. Now we have a converse of that statement, and the converse of that statement says that if you have a point that is equidistant from the endpoints of a segment, then it's on the perpendicular bisector. So in this case, I've got point D, and I know from these two markings that D is equidistant from A and from B, which means that D lies on the perpendicular bisector. So D is on this line CP. So if DA equals DB, that should say DB, then D lies on the perpendicular bisector of AB. All right, so let's look at an example. I know that BD is my perpendicular bisector of AC, and I want to find the length AD. So I know from the perpendicular bisector theorem that D is equidistant from points A and B. So I can set up an equation using CD and AD. I know they must be equal if they're equidistant. So then 3x plus 14 equals 5x. And at that point, it is just algebra. So x equals 7. So if x equals 7, then AD must equal 35. Now, if you want to check that, you could plug in the 7 here, and 21 plus 14 is also 35. Next example. WX is the perpendicular bisector of YZ. So before I go any further, what does that tell me? if WX is the perpendicular bisector of YZ, then I know that XY and XZ are congruent, and I know that W must be equidistant from the two sides, so WY and WZ are congruent. So now I just have to write my answer. WY and WZ are congruent by the perpendicular bisector theorem. XY and XZ are congruent by the converse of the perpendicular bisector theorem, because if it is on the perpendicular bisector, then it is the midpoint. And VY and VZ, well, I know they're congruent by the diagram. So then the next question is V on WX? Well, by the converse of the perpendicular bisector theorem, V must be on the perpendicular bisector of YZ. And since the perpendicular bisector of YZ is in fact WX, then I know that V must be on WX. All right, try these few practice problems. So pause the video and then come back and check your answers. All right, so in the first three problems, we wanted to find the length of AB. So in number 1, that's 15. In number 2, that's 30. And in number 3, that's 55. The next two problems, we are told that XZ is the perpendicular bisector of WY. We wanted to find the length of WZ, which was 23, and the length of XY, which was 10. Okay, a couple more vocabulary words. We'll be using these two, especially in the next couple sections. But concurrent means when 3 or more lines intersect at the same point. So think about a place where maybe 3 or 4 roads intersect, more than just a regular 2 roads crossing. But if you had 2 or 3 roads intersecting, 3 or more roads intersecting, then where they intersected, where the stoplights all were, that would be their point of concurrency. But those 3 streets would be concurrent. Their point of intersection is going to be the point of concurrency. Now, with perpendicular bisectors, they have a special name for the point of concurrency, and that is the circumcenter. So when all 3 perpendicular bisectors of a triangle are drawn, they will intersect at one point, and that is called the circumcenter. Now, we have a theorem about the concurrency of perpendicular bisectors of a triangle, which is the perpendicular bisectors of a triangle intersect at a point, the circumcenter, that is equidistant from the vertices of the triangle. So take a look at this picture. All of the little blue lines that you see, FP, DP, and EP, those are the perpendicular bisectors of those sides. So they bisect the side of the triangle, and they are also perpendicular to the side of the triangle. And P is our circumcenter. But what this is saying is not only is P our circumcenter, but all of these red lines that are leaving P going to the vertices, they are congruent to each other. So I'm actually, So these three red lines are congruent to each other. So if PD, PE, and PF are perpendicular bisectors, then PA, PB, and PC are equal. So we're going to practice drawing the circumcenter, and you need something that can make a right angle, which could just be the corner of a piece of paper. Those are right angles. So if we had a word problem, we're going to kind of follow this word problem. Hot pretzels are sold from the carts at point A, point B, and point E. Where could a hot pretzel distributor be located if it is equidistant from those 3 points? So we want to sketch a triangle and show the location. So the first things we want to do is we want to draw our triangle ABE. So we're going to just connect these points. So now I have triangle ABE. I want to find the midpoint of AE. And y'all should do this with a ruler just to kind of make sure. I want to find the midpoint of AE. Okay, so that's the middle of my segment. And now I want to draw a perpendicular line through this point. It will not, I repeat, it will not go through the vertice. That's a fat line. So there's my perpendicular bisector. I can draw that because I know this is the midpoint. I made sure that this was the midpoint. And I drew this so it would be perpendicular. Okay? So that is my perpendicular bisector of AE. Now, I want you to repeat those 2 steps for BE and AE. So, find your midpoint. And then draw a perpendicular line. Last one, I'm going to find my midpoint. And draw my perpendicular line. Okay, so now you can see that all 3 of my lines intersect at one point. And I'm going to label this point D for distributor, since we're looking for a place for our pretzels to be distributed. So that's a D. And this is my circumcenter. This is the circumcenter of triangle ABC. Now, that's where our distributor should be located. But I want to take it a little bit further, and I want to draw the lines AD. I want to draw the line AD, BD, and ED. So these 3 segments here Those go from my circumcenter to each vertex of my triangle. So I drew from the circumcenter to the vertices. And these segments are congruent. So AD is congruent to BD is congruent to ED. And I didn't mark these, but we made these our midpoint. So I know that the sides of my triangle, where they get cut by my perpendicular bisector, if you want to draw in everything, then go for it. All of those are right angles, and all of the sides have been cut in half. All right, so try the problems below for practice, and let me know if you've got questions. All right, the last thing we're going to do today is a proof, and we've been given triangle ABC and the perpendicular bisectors of AB, BC, and AC. So I don't have a picture, but there's plenty of room at the bottom. So I would go ahead and draw the triangle ABC and draw in the perpendicular bisectors, just like we did in the first steps above. So I had put, what are we trying to prove? We want to prove that the perpendicular bisectors intersect at one point, and that that point is equidistant from our vertices A, B, and C. So if you want a little plan, we want to show that P is the point of intersection of the perpendicular bisectors and also lies on the perpendicular bisector. And then we need to show that P is equidistant from our vertices. So we'll start off with our statement 1, which was our given, that we have a triangle, ABC, and we know that the perpendicular bisectors AB, BC, and AC. So our next step, I know that my two perpendicular bisectors must intersect at some point P. Why do I know that? Well, I have a triangle, so its sides cannot be parallel. Therefore, if I have segments that are perpendicular to them, those perpendicular segments cannot be parallel. So the perpendicular bisectors must intersect at some point. And I'm just going to call that point P. So I want to draw PA, PB, and PC, which would be from the circumcenter P to each vertice. Why can I draw those? Because through any 2 points, there is exactly one line. So if I have point P and point A, then I can draw the line PA, or the segment PA. So I know that PA equals PB, and I know that PB equals PC because of the perpendicular bisector theorem. I have a perpendicular bisector, so I know that it is equidistant from the endpoints of my segment. Well, if PA equals PB and PB equals PC, then it stands to reason that PA equals PC by our transitive property of equality. Well, if PA equals PC, then P must also be on the perpendicular bisector of AC by the converse of our perpendicular bisector theorem. P is a point outside our segment, but it is equidistant to the endpoints of the segment. So, therefore, it must lie on our perpendicular bisector. So now I know that all three of these little segments, PA, PB, PC, are congruent, are equal. So P is equidistant from the vertices of the triangle. And that's our definition of equidistant. We are the same distance from at least two figures.